Hi, everyone. Thank you so much for joining our live webinar today. My name is Julie Tran, and I am the Digital Marketing Manager at NH Research. I will be your moderator for today's session. Today, we are very excited to have our speaker share best practices on how to simplify and accelerate battery testing, including a live demonstration using our Enerchron test management software. Now, before we get started, this presentation is being recorded and will be sent to you after the session is over. Please submit your questions in the toolbox to the right of your screen, and we'll try to answer as many questions as we can at the end of the presentation. If we run out of time, we'll make sure to follow up with you. And also at the end, there will be a brief survey. We would really love it if you could complete that survey so that we can provide you with informative content and continue to support your needs. I'd like to introduce our speaker, Martin Weiss, who is the product director at NHR. Martin has over 25 years of experience in testing batteries and building automated test systems. At NHR, he is responsible for developing new hardware and software test solutions. Martin has extensive experience working very closely with our customers to develop strategic battery test plans for specific applications across industries. So we are very pleased to have him share his expertise with you today. With that, Martin, I will be handing it over to you.
Thank you very much, Julie. Well, it's my pleasure to approach or address you guys today, and I am Martin Weiss with NH Research. NH Research as a company focuses on enabling electrification. And what we mean by that is we accelerate the innovation, validation, and functional testing of both today's and tomorrow technologies. We achieve that by offering the best-in-class in performance, products that are very easy to use, and that are modular and scalable solutions, allowing you to reduce your testing time, improve safety, and with regenerative products, actually recapture some of the energy stored in your products. Our world-class test solutions is a wide product portfolio, including battery and fuel cell test systems, bidirectional DC products, grid simulators, AC and DC electronic loads, AC and DC power sources, and so on. We truly are your partner in test. In the last webinar, we talked about different ways or flexible control options for our cyclers. Everything from the manual modes shown on the left here, such as our touch panel interface and remote control, or that you can automate the system with your own software through LabVIEW or using our drivers. And today, I'm pleased to demonstrate for you our sequencing software package called Enerchron. Enerchron, as a test executive, provides a very, very easy to use way to create extremely complicated software sequences without having any software experience whatsoever. So I'm looking forward to showing you a few examples of how Enerchron does this. As we look at our main agenda, we're going to first take a quick look into Enerchron and just cover it at a high level. So what is Enerchron and how is it different than, say, some traditional cycling software packages? Then we'll take a departure from Enerchron and just describe the battery testing process, covering the challenges and what it takes to build a robust test plan. This will give us the foundation we need to actually build a couple of test plans, such as a simple battery test procedure and showing how variables can be used, or even a drive cycle. So let's start off. What is Enerchron? Well, simply put, Enerchron is our test executive, and it's a way that allows you to simplify and accelerate your battery testing. It does this by providing an easy-to-create interface where you can create those sophisticated test sequences and not even require prior software experience. The sequences can even be highly dynamic, even scaling or using battery management data or drive cycles or combinations of any of the things needed to meet your particular test goals and adjust themselves using these variables and formulas while the test is running. And then we provide a configurable reporting engine that allows you to eliminate post-processing and even calculate some of the necessary results during the test. We are breaking the mold with that extensive use of variables and formulas, allowing you to use variables and formulas all throughout the test sequence, not just in specific locations. It also provides an intuitive test environment for each of the different types of users. For example, an operator may not have any technical background, but he loads a test execution interface and can simply start and stop the programs. Or through Enerchron, it's possible to create custom user prompts that helps guide the operator through his particular job, again, removing any need for the operator to have additional technical training. The test developer is given a test sequence creation interface and also can then create these custom user prompts throughout this interface. This is where all the logic and the sequencing pattern are implemented to create the test procedure. There is an administration function where you can manage the user levels. Are they developers? Are they operators? Or are they even promoted to administrators? And then also give access to various interfaces. And through system security and naming of products, you can actually control the entire lab environment as an administrator and do anything at the developer or operator level as well. Again, for the most part, we're going to be taking a look at that developer's interface, or the way that a test sequence is created. Battery testing is becoming much more than battery cycling. When you look at competitive systems, you'll find that their actions, or what the step can do, is usually related to a charge, discharge, or rest. Some companies will even try to make it look like they have many steps by making variations on these themes. This is a C rate discharge or other forms of discharge, but really they're just simply charge, discharge, and rest. We can do this using our operation function, which provides that same level of function. But you can see in our action list, there's a wide list of additional actions. These are there for controlling things like electronic load, power supplies, grid simulators, chillers, temperature chambers, or provide user interfaces such as notification windows or prompts, or even communicate with other devices such as other test equipment or third-party devices, battery management systems, by using CAN, Skippy, LAN, Serial, Modbus, and so on. There's a very, very wide portfolio of available actions where any one step can do an array of things. This helps us to produce a true energy test solution rather than just purely a battery cycler. By this, we're actually able to control through Enerchron, shown in the upper left-hand corner here, not only the cycler, but communicate directly to the battery or the BMS or third-party devices such as chillers or chambers, as well as then control relays, measurement sources, or other test equipment needed to build that comprehensive test solution and make the battery or the unit under test feel like it's really in the vehicle or the application environment. The test developer creates his test sequences using this interface. Here we can see that there is a sequences tab, and right below the sequences tab is the main sequence. All of the steps are organized as rows in this table, and the description of each step, including a name or label, what the step does, the action and action data, when the step is considered complete, and what step would be next is end conditions. Any jumps within the sequences are graphically indicated with a branch. And then there are both report controls and comment features allowing the test developer to document his code or the data from the test results. Again, you can use variables or formulas pretty much anywhere that you would have typed in a physical value or a string in the sequence environment. It's this use of user-defined variables and the way that we've constructed the end condition wording that allows you to match the written procedures extremely precisely. You're using your terms and your logic and matching that to the words in the sequencer rather than having to learn a new language. By using variables, you can also do some very interesting dynamic things, such as keep the source files or drive cycle from the standards in its unmodified form, and then dynamically scale it step by step. You can use these variables to input information from the user or display information to the user or operator throughout the test sequence itself, and then calculate and store results directly inside the test sequences. It's this ability to use variables or formulas anywhere you might have typed in a value in a traditional battery test system that sets Enerchron apart and allows for tests to dynamically scale for different test functions and even for different unit under tests. When you consider a traditional programming, if I needed to do something simple like a pulse discharge test or discharge a battery at its rated rate of current, normally for most cyclers, you actually have to produce a different test, even though it's for the same basic function, that's scaled appropriately for each different application or for each different battery. That combination can produce a matrix of hundreds to literally thousands of test programs. But when you have hundreds or thousands of test programs, how easy is it to make a mistake? How easy is it for the operator to make the wrong choice and apply the wrong test program to the wrong unit under test? Or to have a bug that crept somewhere into the creation process that's now been copied and replicated between the test programs? So how much does that actually cost you to have a lot of test programs? How much time and how much effort? Is there a benefit to actually taking thousands of programs and collapsing it down to where it's really one program or only a handful of programs, so the operator can just select the one program, run it, and know that he's going to get the right results every time? As an example of this, being able to provide the operator a customizable interface, interface that actually meets your business process needs. So you can use these interfaces to do things that you can't do with traditional cyclers, such as creating a workflow instruction or a series of user prompts that guide the operator through the steps that you want him to take, with a picture and a written description of each step. He presses next, then the next user prompt comes up and gives him the next step in the testing process. Or, as shown here on the right, being able to add scaling factors or scan a battery barcode. So that way information is provided by the user that the sequencer can use then to adjust itself to do the testing. As shown on the right, a drive cycle program and even running this multiple different drive cycles can be as easy as 1, 2, 3. The operator loads the program, provides an appropriate scaling factor for the unit under test, and then selects a button which says which drive cycle does he want to use. We'll give you a demonstration of this later throughout the training. But it's through variables that you can dramatically improve productivity and eliminate operator errors, because the operator interfaces actually match the way you intend the operators to use the system. We do get a lot of questions about how do I get my test data out of the system? And with all sequencers, there's some form of reporting engine. It's not uncommon to have one report that has all of the data in it at some data rate. What we have done is not only provided the ability to have that traditional style of reporting, but to actually break the report up depending on how that report is intended to be used. For example, because variables can calculate results and can be logged to a file, we can create a report, as shown on the left, which is only containing the logged messages or the logged variable values. So in this way, you can have a report that has only the key data that you felt was necessary and eliminate all of the extraneous battery data. You can also activate the same type of report having a low resolution of battery data, so that way you can see the battery curves but in a format that's easily graphable in Excel without requiring additional post-processing just to shrink the data down. And for those moments that you want high-speed resolution or you want a periodic summary report, such as like a per test, a per cycle, or a per week report, you can also create a new, as shown here, per loop report, which then gives the higher resolution detail and the report is completed each time through the loop, giving current information, allowing the engineers to verify that the test is running correctly. It's through these multiple report engines that you can save time and dramatically improve your data visualization during the test itself. So the variables and formulas, especially being able to use variables or formulas anywhere throughout the test, provides a dramatic way to simplify and even accelerate the battery testing procedure. It provides an ability to do dynamic controls throughout the test and even to have user prompts where the user provides key information that allows the reduction of duplication of tests and the automatic scaling, such as that drive cycle example we saw earlier. We have a number of other features, but the one that I'll point out on this list that we won't cover in too much detail through this webinar is a way to remap the test sequence, saying what other systems are set up to be equivalent to this existing test system that the test was created for. We've heard many reports of sequences on competitive packages that seem to run when you select a hardware set, and then you find out later that maybe you used a 25 amp channel when the test required a 50 amp channel. So the test tried to run, but it limited all the currents to only the hardware capability, resulting in bad data and a requirement to rerun the test. Our program remapping capability makes it easy where the operator is given the choice. Do you want to run it on this station or this station? And the stations that are not viable are automatically blocked out. So when we move forward into our agenda, let's talk a little bit about what is a battery testing process. What are some of the challenges? And what methods can we use to actually build a robust battery testing plan? Battery testing is a process, and it's very similar to many processes, even a process like travel. When you travel, there's some stuff you can control. Once you've decided that you intend to go to a location, which is your main objective, do you choose to fly? Do you drive? Do you want to take a train? There are different ways to get there, and those are something that you can control. You even have the next level. So if you decide that you're going to drive or fly, which airline are you going to use? Are you checking bags? Are you only going to use a carry-on? These are decisions that you can control. And some stuff takes just as long as it actually takes. If I'm flying from California to New York, the amount of time it takes to fly from California to New York is about the same amount of time, regardless of which airline I use. When I get to New York, the amount of time it takes to get my bags out of baggage claim is the amount of time it's going to take. There's nothing I can do to actually make that part of the process go any faster. When I do go to the airport, there's also processes involved in doing something like flying. And I kind of need to follow these steps in orders, or it can cost me time. And if I make a big mistake, it can cost me a lot of time. For example, I do need to check in, but do I check in on the counter? Do I do it online? Do I have bags that I need to do the baggage drop process, or can I just skip that and go straight to a security line? Which security line? And then how do I go through the security line? There's a difference between the standard traveler and, TSA PreCheck, for example. When I get on the plane, different airlines have different processes for how do they line up their passengers and get them on the plane. When you make a mistake, like if I go to the wrong airport or I'm at the wrong terminal, I might miss my flight. And that can result in a significant amount of lost time. And so it's important to take the steps of any process in order and understand the flow that's necessary. All of these are very similar to the challenges in battery testing. The testing itself can take a long time. If I set a step to discharge a battery from full to empty, and it's set to discharge at a 5-hour rate, it's going to take 5 hours to discharge that battery. Unless I can change that rate somehow, that step is something I don't have any control over. It will take 5 hours. While that step is running, I may be collecting voltages and currents and powers every second or even faster. So there's a lot of data that's collected. And if I find out after I analyze the data that I made a mistake and I discharged at 4 hours or 6 hours instead of the 5 hours I'm desiring, then that's an error in the test. If that error invalidates the entire test, I get to do the whole thing over again. And so it's very important to make sure that we understand the test process and the procedures, and we do everything in our control to control the factors we can, to minimize the mistakes, and to get the testing done as efficiently as possible. This leads us to what are the best practices to develop a robust battery test plan. And developing a battery test plan is just like taking a journey. The first stop is to define the end goal or the objective. If we don't know where we're trying to get to, then we can't really make any of the other necessary decisions. But let's consider if I wanted to measure the capacity and establish a state of charge or how full the battery is once I'm done. That could be an end goal or an objective. The next stop then would be to define all of the steps in detail. This can be in a written form, as shown on the left. This could also be in a flowchart form, or both. But what are the steps? What would I do step by step to actually achieve my end goal? If I look into each step, I can define all of the terms. And by looking at the terms that I use, these terms will become my variables. And then once I take a step back from my process, it's important to look at it and say, is there anything that I should have my test stop immediately? What are the conditions in which the test should stop? For example, safety reasons. Not how does it stop, but just what are those conditions? And when we identify those abort conditions, those will become our safety limits. And then we will define another sequence, such as what does it mean to safely stop no matter where I leave the test sequence? And this becomes our abort sequence. I know that sounds like a lot, but it's actually important to make sure that you get these details done. If I look at a written procedure, it would seem like, well, there's a lot of steps and there's a lot of words, so this is seeming to be complete. But even from national laboratories, such as the Pacific Northwest National Laboratory, out of their protocols for uniformly measuring the performance of energy storage systems, or ESS, when we look into it, we see that most of the steps actually require further definition. For example, the energy storage system needs to be discharged to a minimum state of charge in accordance with the manufacturer's specifications and operating instructions. This doesn't actually even tell me how to do it. And two different products, even from the same manufacturer, and two products from two different manufacturers, most certainly, will have differences in how the discharging is to be done and the level that is considered the minimum state of charge. So I need to use this as a reference to actually get more information and develop my test procedure to make sure that I have all of the steps in place. If we look at all the way down into step 6, we also see that the battery data, as in the individual voltages and currents, all the way throughout the charging and discharging, is not even required at the end of this test. But the actual battery knowledge is just a calculation from a number of the cycling patterns. How many times have I run this discharge? At least 8 times. And then looking at an average and a standard deviation of the amount of energy that has been passed to the battery or energy storage system is the result of this test. So again, the devil is in the details in how to conduct the steps, in what data is actually needed, as well as what safety should be applied, because there's nothing in this written procedure that describes safety or making sure that you have your laboratory as safe as possible. How we encourage people to think about safety is through layered safety approaches. For example, the first layer is always through your logic design. And so being able to say, in this condition, if this happens, I want to stop. This can be done on a step-by-step basis and even use battery information, such as battery management system or CAN data, directly in the sequence logic itself. You wrap the sequence logic with a global set of sequence logic that runs in its own separate thread. For us, this is our safety tab, which then takes the abort conditions or the global cases and says, if any of these things ever happen, then I want to run the abort sequence and shut down safely. And again, using battery management data or CAN data is usable in this layer as well. We then have wrapped those programming layers with a number of hardware layers that can be implemented, such as hardware limits, acting like programmable fuses, external interlocks and EPOs, allowing an external device to also shut the hardware down if it monitors something, and of course the communications watchdog. So if there's any communications loss, then that overrides all of the other things and would shut down the system as well. With these ideas in mind, we're actually ready to start going on the journey and developing a simple test procedure. We're going to develop one using variables, just so that way you can see how variables can be used in the process. So, our first stop, what's our objective? Well, earlier we introduced the idea of let's measure the capacity and establish a state of charge, and let's use it based on the C rate. And if you were in the last webinar, the fundamentals of battery, you realize that C rates is a way to normalize the test without having to describe, is this so many series cells or is this so many parallel cells, but will provide kind of a time-based way to normalize the test regardless of the battery configuration. Now, if we happen to know approximately how many gallons a bucket of water can hold, ballpark, then we can get it more precise by following the process of filling the bucket until it's full, emptying the bucket, and carefully measuring how much was in the bucket itself. Then we know exactly how much that bucket can hold. And we can put back 30% of that or 50% of that, and we would know that that bucket is 30% full or exactly half full. This is the exact same type of analogous process that we use to measure the capacity of a battery, because you can't simply look inside and see how full is the battery. So our next step is to define the test procedure in terms of all of the individual steps that are used. For example, step one would be to charge the battery until it's full. Now, from the manufacturer, they would say to charge the battery up to a constant voltage equal to the maximum voltage and a current equal to the capacity of the battery divided by 3, or a 3-hour rate. And then we do this until we reach the maximum voltage and the current is tapered off to C over 10 or C over 20. In this case, we'll use C over 10. As you can see, that's what is written in the step on the left-hand side. And on the flow chart, we would have a process block or our action that says enable the charger, and here's the setting, along with the triangles or decision. If we're not at the maximum voltage, we keep looping around. And when we reach the maximum voltage, are we at the current of C over 10 or less? If not, we continue to loop around. And otherwise, we go down to the next step, which would be to discharge with a current of C over 5 until we reach the minimum voltage. In this particular step here, this will take about 5 hours to complete. And there's nothing we can do to speed the process up. It doesn't matter what size the battery is, whether it's a very large battery or a small battery. This is telling me that this is a 5-hour step, because we're discharging from full to empty at a C over 5 rate. We then would record the capacity, which is actually very easy for NH research because there's a measurement that's in the hardware itself. So we just set this to a variable. And then we can set the system to recharge until we reach that desired ratio, or the target SOC, the target state of charge, and then turn off the cycle. So these are the detailed steps, including all the decisions that are made. Now we could further extend on these by adding in battery information or other safety features. But to keep it simple, we'll keep it just to these steps for right now. If we look into the flowchart, there's a number of terms. The maximum voltage, and depending on the battery pack, that may be a different value. Or the C, what's the total capacity that's assumed for the battery? Is it a 100 amp hour battery? Is it a 10 amp hour battery? Well, what is that initial value estimated? What's the minimum voltage? How far down can I go? We'll need a place to store capacity, when we actually need to record the number of amp hours. And then we use that in the formula to say, where do we want to get? 30% full or 50% full? These terms become Enerchron's user-defined variables. If I open up a live instance of Enerchron right here, you can see that there is a sequence tab, a measurements tab, and a variables tab. These user-defined variables allow us to put these names along with their initial value directly in the test sequence itself. And then we can use these throughout the test sequence. If I slide it over and select the Sequences tab, the Sequences tab contains the logic. For example, being able to set the operation of the hardware for the power module, enabling it for charge, with a voltage setting equal to the maximum voltage, and a current setting equal to C divided by 3. Again, being able to use the terms and the formulas directly inside the test. If I look at the end conditions, just for this one step, we can evaluate if the measured voltage is greater than or equal to the maximum voltage, and if it is, then also evaluate if the measured current is less than C over 10 before going to the next step. So it would stay in this charge state until reaching those end conditions. As you can see, the sequence has the main, and we'll come back and see the abort, but then we can use measurements as a form of variables, information from CAN buses, or even test information, which is a pre-test prompt, as data or measurements and variables and formulas anywhere throughout the test. If I try to save this program, it's going to give me some warnings. It says that the safety tab, limit, does not contain any items, that the abort sequence does not have any steps, and that I'm using a power module, but I haven't activated the hardware safety feature inside the power module. Let's return to the presentation and consider what some of these things might mean. Oops. Go back to the presentation. There we go. So as we were talking about that robust process, the next stop was to define the abort conditions. These are globally, is there anything, or even down to the individual step, but is there anything that we should say, let's stop? Examples of that could be, does a step take too long? If the step is never completing, maybe we want to stop the test. Or have we measured an unsafe voltage, current, or power? Is it too high or too low? If we have tied in the battery management system, and the battery management system says there's a problem, voltage, current, power, temperature, even a fault code, do those say stop the test? Once I have this idea of what these are, when do these conditions apply? If they are global, anytime they happen, that is a layer 2, type of sequence safety, and would go inside of the safety tab. If there's anything that should stop just a specific step in the sequence logic, then you would add that into the flowchart, and that really becomes a layer 1, and you can optionally add it into a layer 2. Now, for some of these conditions, maybe you want to actually have the hardware trip or detect this and shut off. This can be done then through programmable safety limits, which was the final warning, a layer 3, or through external means, such as signaling for interlocks and e-stops in layer 4 or 5. But again, what we're asking ourselves is, what would cause an abort or a reason that we need to stop? And then finally, we need to define, well, what does it mean to stop safely? So from any test or any step inside the sequence, if I'm running that step, what would I want to do to make sure that the test ends safely? I might not just want to turn off the cycler. I might want to first change the temperature chamber or adjust current levels or open up a relay. But the sequence of events that allows the system to shut down safely is another process and goes inside the abort sequence. So if I return to the sequence here and I say, okay, let me close this error or this safety issues detection, it's going to open up the safety tab for me and make a couple of recommendations, such as if it detected any hardware errors, then it will also try to act on the safety shutdown sequence, or if a step takes longer than some amount of time to complete. Now, being that system step time is a second timer, we know that there's a 5-hour step. But if that took 7 hours for some reason, that's way too much time. So instead of getting out my calculator and typing, 60 minutes, seconds in a minute, and 60 minutes in an hour, and 7 hours is 25,200 seconds, I can simply type, I want 60 times 60 times 7 right here in the step. And it will automatically calculate that formula when it's needed to come up with that right answer. Instead of one of these physical numbers, I could have actually applied a variable instead by selecting one of the user-defined variables in the formula, and then it becomes a more dynamic value. We then would also need to go to the Sequences tab and define underneath the abort what conditions or what would actually cause when a safety abort is triggered, either through the Safety tab or the operator pressing abort. What do I want to do about it? In this case, I think we just want to take the power module and ask the power module to be turned off. So now that we've developed a simple driving sequence, and actually there's maybe one more thing that I probably should have covered. If I wanted to adjust this battery test sequence, I could change this battery test sequence just by adjusting the maximum voltage value, the C value, and the minimum voltage value, and rerun the same test program for a different size battery. In the next process, we're going to show you how we can actually do some of those things by providing user prompts or other ways to help to automate that. So let's look at building a more complicated pattern, which is actually implemented quite easily, and then extending it by giving things like user prompts, by creating a simple drive cycle sequence. Firstly, what is a drive cycle? Well, simply put, a drive cycle is a pattern that's stored in the file that's used to represent some real-world usage case or pattern. Driving a car, even in the city, is different in the United States than it is in Asia, than it is in Europe. And so there are pattern files called drive cycles that say, if I'm using a passenger car in different regions of the world, how is that pattern different? Highway driving is different as well. And there are different types of vehicles. In the United States, we have a big desire for large vehicles, such as SUVs and trucks, and can use these to tow very large things, such as boats, which is not as common in some of the other regions of the world. Drive cycles are not specifically limited to electric vehicles. There are grid cycles simulating behaviors of the utility grid. There are also flight profiles, which then simulate the flying characteristics of an airplane and how power is used when an airplane is used in a particular test case. As you see, the drive cycle on the right, or the Federal Urban Drive Cycle, is really built up as a CSV or a file with lots of numbers in it. In this case, 1,400 individual different settings. And so it's not practical to program this step by step inside the sequencer. It's better to bring in a standards-based file and use this as a way to create the drive cycle. Now, the standards-based file itself, as shown here, is unscaled and uses a percent of the peak discharge power. Inside the file, there are numbers, such as the time that the step is supposed to happen and the scaling factor. And if I were doing this manually, and I just completed step 44, then you would go back to the file and say, I just did 44, what's next? 45 is next. Okay, and the scaling factor is this minus 50 or 0.5038. When it's time to do step 45, I do it, calculate the answer, and set the hardware. Then I come back to this file and I say, what's the step after 45? Oh, the answer is 46. And I get this scaling factor of 0.55823. I would continue with this process until I've defined or found that the last line of the file was actually found, and that tells me that the file is complete. Using what we just saw there, we could build a simple drive cycle process, such as starting the cycle timer or initializing the variables that we need, get a line from the file, and then wait until it's time to go. Once it's time to go, we could calculate the power. And then based on the sign, is the request positive or negative, we would set either charge or discharge to the calculated power. We then could say, well, is this value less than the last line of the file? If it is, we go back up and get the next one. Otherwise, we consider the cycle complete. And this then is a simple description or diagram of the steps to complete a basic drive cycle process. Sorry, got ahead of myself. I need to open the sequence. Here again is a live example using a sequence editor showing that we're going to implement the drive cycle process. In this case, I put it in as a subroutine, so that way there could be any number of steps before running the drive cycle, such as preparing the battery, getting it to temperature, etc., before running the drive cycle. And then from main, I also set it so that way I can put different cycle types or different scaling factors by adjusting just this one variable, and the whole process would run completely. And then say, can you please go do the drive cycle, and when complete, come back to this process. Or maybe I do some additional steps, or simply run the abort sequence. The drive cycle process, or sequence, then, mimics this flowchart here, where we initialize our variables, we ask for the next line in the file, so find me the first row in column 1, which is greater than the last time I looked, and store that from column 1, so that way the next time I look, I get the next step. And from column 2, store the set value, and also store for me whatever the last value in column 1 is, so I know that I've ran to the end of my file. We don't have to go through all of the logic here, but you can see that we would just wait until it's time, or the cycle elapsed time has met that file time, and then calculate the power and set the hardware. And then decide, do we go back up, or are we returning back to the main process? This gives us a very easy and simple way to automatically scale using the formula, which brings in whatever the file had to say and the scaling factor to calculate the right power level to set to the hardware. Now, what if we wanted to kick it up a notch? By adding a custom interface, so that way we could give the operator a way to test different size batteries. Now, this interface could use a barcode, potentially, and even use this lookup from file to get the test parameters from a test control file. Or what if we wanted to just let the operator choose from different drive cycle patterns that have different lengths or different scaling factors and different patterns, such as the US06 or the WLTP or JC08 or other driving patterns. If we gave the operator these types of controls, is there anything else that we could save through eliminating duplicate tests, or making our testing process more consistent, or that we could improve by reducing operators' errors because they always end up using the same operating screens? we can implement this type of prompt directly into our sequence example here. So instead of using set variables to set cycle type and the scale factor, instead I'm going to choose to make a user prompt. I've already built the prompt, so I'm going to import the prompt from a file. And here we see we have the scaling factor. And when the operator fills in this information, this will be applied to the scale factor variable. Then there are a number of buttons here. This button is named US06. This button is named FUDs. And when the button is pressed, it will return the button pressed to cycle type. This then allows the operator to select the scaling factor and the drive cycle by simply typing in a scaling factor and press the button. The only other thing I would want to do in my sequence is deal with the cancel case. So if the cycle type equals cancel, then we would want to go to next step. So we skip doing the drive cycle process. This test sequence is now complete. As long as there is a US06 file, a FUDS file, an NEDC file, an EUDC file by name, .csv, when the operator selects one of those buttons, it will run over to the drive cycle process and then automatically open the appropriate cycle type file and run through the same process, even though the different drive cycles may have different length and duration. It will run them automatically till complete and then return to main. This is very different than traditional cycling packages, where you say, here's the file that I want, and it must be pre-scaled, and it has to be in a certain format, and we have to let the step run for the amount of time that the specific file was created for. So what all did we learn today? Well, a comprehensive battery test solution is becoming much more than cycling. It requires being able to deal with various hardware and software pieces, such as using the CAN data, using BMS data, and directly adjusting other things in the environment, such as chillers, chambers, and do that based on the information of what's going on with the battery at any given time. This is a strong thing for variables. And Enerchron can easily create these test sequences, and then by using variables, even reduce the number of test systems or test programs that are created or even needed. You can customize the operator interface, which improves productivity and further prevents errors, and further eliminate or reduce the post-processing by using the variables to calculate what you can while the test is running, and by giving you the data through the configurable reports. It's through these ways that we can control those factors that we have direct control over and accelerate the battery testing automation. There's a large number of resources available on our website, including some of our cycler hardware, our test executive brochure, the fundamentals of battery white paper, which was the basis of our last webinar, as well as links to our previous webinar. And you can schedule a consultation with one of our technical experts. I'd be very happy to show you how do we infuse CAN directly into test sequences, or how can we do very comprehensive test programs in very simple numbers of steps. So at this point, I'll thank you for attending and turn it back over to Julie to see if she has any questions that we might need to answer.
Thank you so much, Marty. I just want to remind the audience that they can submit questions using the toolbox to the right of your screen, and we will make sure to answer as many as we can or follow up with you. So the first question is, you did talk a lot about battery testing and how it involves much more than just cycling the battery. Can you share customer examples of how they're using external equipment and why it's important?
Sure. The two that come to mind right offhand are different ways that temperature environments might be being dealt with. One of our customers had an old temperature chamber that's long since been out of manufacture, but was still functional. It happened to have a computer control interface. And so by sitting down and using our communication functions that are inside the sequencer they were able to find a way to not only control the chamber, such as turn it on and off, but dynamically control the chamber, having it ramp up and down throughout the test sequence for a piece of equipment that you can't even buy today. Similarly, we have another test lab over in Europe that had to adjust the coolant temperature as an offset compared to wherever the battery temperature is now to try to accelerate the testing or getting the battery to either a hot or a cold temperature. Had they only set the battery to the desired temperature, it would be very, very slow in getting there. But they could safely raise and lower the battery temperature quicker by setting the coolant temperature to an offset of whatever the current temperature is. This means that you're actually reading from the battery management CAN data, calculating a value to tell the chiller what temperature to use as the next setting, and then looping on that process to get the battery to temperature faster. So in these ways, we can directly accelerate the test, and it requires a lot more than just simply cycling the battery or charging of the discharge of the battery.
Thank you. Now, this is a question on our technology. How does your test sequencer technology differ from traditional battery cyclers?
Sure. So one of the things that you will find in traditional battery cycling is they tend to focus very much on battery cycling. And so the steps will be charge, discharge, rest, or a variation on this theme. Charge with CCCP or charge with CCCV, or something that's simply charge, discharge, and rest. As I just described in the other case, I want to get the battery to temperature. How do I do that if all the steps are charge, discharge, or rest? And how can I make it go faster? Even if the manufacturer allows me to deliberately put a little higher temperature to get the battery to warm up faster, if all I can do is charge, discharge, or rest. You can't. And so by making a more general purpose sequencer that has many of the same programming capabilities of LabVIEW, but without requiring you to understand how to build drivers, how to build the sequencing logic, and how to build the data reporting system, you get all of the power of a programming language, but without the complexity that requires programming skills.
Okay, I do see a few questions about BMS and CAN data. How could someone incorporate that data into the test?
Sure. As we went through the presentation, there was a moment when I highlighted each of the tabs, the sequence tabs, and then there are multiple variable tabs, measurements, for example, something that comes from a piece of test equipment, such as a cycler, the user variables, and one of those tabs is the CAN tab. In that CAN tab is where a DBC or a database file can be loaded, which describes the signals or the pieces of information that are transmitted in the frames or the packets of data across the CAN interface. Once described, you would just say, which ones am I listening to out of the entire database? And those become variables, which then can be directly used in many of the test steps and can also be used in user variables to create formulas, end conditions, settings, etc.
Okay, and you had described some best practices for developing a strategic test plan. What would you say takes the longest amount of time in creating that for an application?
Sure, it's a very good question. Oddly enough, getting everybody to agree to what something means, something simple. For example, if we're going to charge the battery till it's full, you'll often end up with very, very different opinions as to what's considered full. Is it when the battery management system says it's full? Is it when the current tapers to a certain value? Is it only when I reach a certain voltage? Do I get to a certain voltage and hold it for time, or do I watch for current? And strangely enough, even when I go to major test laboratories, this is where we end up spending the majority of the time, is just getting agreement on the individual steps of the process. Once the process is detailed, the implementation of the process, even making the process highly dynamic, is actually very easy and takes very little time.
Oh, sorry. I'm just looking through the questions here. We do have a handful of questions, but they do seem maybe more appropriate to get into one-on-one individually. So we will follow up with you after the webinar is over. And actually, that does conclude our webinar and presentation today. And I just want to thank everyone for your time. If you have any questions, please feel free to contact us. We're here to help. You can visit our website for future webinars or events. And Martin, thank you so much for your time as well. At the end of the presentation, there will be a survey. If you could please take a moment to fill that out, we will definitely try to create more content to support your needs. Thank you all. Have a great day.